Well, as we move toward greater and greater capability to do quantitative calculations, it turns out that we need to emphasize a very important aspect of the relationship between concentrations, pressures, and one other very important variable, and that's activities. And the point of activities is that when we write the expression for entropy, we know that that's equal to the entropy under standard conditions minus R log P divided by some standard pressure. And we have typically written that under standard conditions, P is equal to 1 atmosphere, which is equal to 1 bar, to a very close approximation. So when we put that value of P into the denominator, it appears as a quantity 1, and that means that we can rewrite this as the entropy under standard conditions minus R times the log of P. Except we have to be careful about one thing, and that is that when we wrote log of the ratio of pressures, that quantity had to be unitless because pressure occurred in bars or in atmospheres or whatever, but it must be unitless. So when we now write this where our standard pressure is 1 bar, we write this as log P, but we've done something very important. We've divided this through by a standard reference state. So the activity A, which turns out will be very important for equilibrium calculations, is the effective concentration or the effective pressure of a substance divided by the effective concentration of that substance at the standard reference state. And I can apply pressure equally. It doesn't matter if I'm doing this by concentration or by pressure. But the key point is that the activity has to be normalized, that is divided through by that standard state. Now we've already done that automatically with our pressure assignment. We have defined that standard state as 1 bar. We divided through, and lo and behold, that other pressure, that is the standard pressure, dropped out of the expression. So we already know what our reference state is for gases. It's 1 bar, giving us exactly the expression we've already done, but also for concentrations in solution. In solution, if I take a 1/10 molar, that means that I've got 1/10 of a molar divided by 1 molar. So my standard state is 1.0 molar. So I have to divide that concentration into the quantity that I insert into that expression for the entropy change. But it's exactly the same principle as we use for pressure. So there's the standard for solution concentrations and there's a standard for pressures. Now if I have a heterogeneous mixture, that is I have liquids and solids, I set A equals 1. And I set the activity equal to 1 because as long as I have some of that pure liquid or some of that pure solid, I can ignore its concentration because it's the chemical relationship between the gas and that solid or liquid that matters. So if I have just a tiny amount of that liquid or solid there, that's adequate to establish the equilibrium. So for pure solids and liquids, that activity is simply equal to 1 when I'm inserting that into the expression for Q. Okay, so now just to finish off, gas is measured in bars, and for solution, the activity is equal to the molar concentration divided by 1 molar. But there's something very important about activities, and that is that activities allow us to calculate exactly what the equilibrium constant is under equilibrium conditions, which is a thermodynamic state. And we always represent that as K sub EQ, representing the fact that we have calculated it. We've calculated the expression based on activities. And so I can write this as the activity of the products, C, raised to the stoichiometric coefficient times the activity of D raised to its stoichiometric coefficient divided by the activity of A and of B. So I have exactly the same expression based on the law of mass action, but I've now inserted activities in that. But the key point is that that equilibrium constant I can then use in all thermodynamic calculations. And on reflection, you could easily make the case that we should start out the entire analysis of Gibbs free energy, of Q, of K, based on activities, because that guarantees that we have the right quantities inserted into those quantities. We developed it from the point of view of concentrations and pressures because those came directly out of analyzing a chemical reaction. But when we get deeper into thermodynamics, it turns out these activities are extremely important. So let's just review this to emphasize how much progress we've made. We now have derived this expression with which we can calculate delta G under any conditions. That is, I can take the Gibbs free energy surface from reactants to products, and I can sketch it out for whatever the shape is, but I can calculate that delta G at every single point along this connection between reactants and products. And we also now know that we can represent entropy as entropy under standard conditions minus R times the log of the pressure divided by the standard pressure, that is 1 bar. And so we have elevated the concept of activity, which is defined by the ratio of the concentration of a substance to the concentration of that substance under standard reference conditions. So when an equilibrium expression is written in terms of activities, the equilibrium constant is a thermodynamic equilibrium constant, and we can use it in any formulation that relates to the thermodynamics of an equilibrium condition.